Greetings everyone. This is Sajjad Talukder, student of Department of CSC at Premier University Chittagong, Bangladesh. It is my pleasure to be part of the 11th International Conference of Informatics, Electronics and Vision hosted by the University of East London. It is indeed an honor for me to present on this global platform our research that helps empowering Bengali language in drone control with artificial neural networks. Before we dive into the details of our presentation today, let's take a quick overview of what you can expect. Our presentation will cover the following areas as you can see in the slide. Let's move into the next slide. As we all know, in the fast evolving landscape of the technology, drones have become indispensable across various industries, from agriculture to urban planning to modern warfare. However, they have often been challenging to control, requiring a specialized knowledge and complex interfaces that pose a steep learning curve for users. That's where innovation comes into play. We have envisioned a future where controlling drones becomes as natural as having a conversation. Our objective is to find a smooth and efficient solution that's not only intuitive, but also accessible to a wide range of users, irrespective of their prior knowledge of drone operation. What makes this journey even more exciting is our choice of language, which is Bengali. As the 7th most spoken language globally, with the millions of native and second language speakers, Bengali represents a promising medium for drone control. Surprisingly, despite this potential, there's been a clear absence of prior research in this area. To tackle this challenge and offer an intuitive approach to drone control, we turn to artificial neural networks, which play a pivotal role in identifying and classifying complex patterns in data. With the ability to adapt to different accents, process intricate voice commands, and handle nonlinear audio data, ANNs are indispensable in achieving our goal of accurately recognizing and classifying voice command. So here's the objectives. Our objectives are clear. We aim to investigate the feasibility and the effectiveness of using Bengali as a medium for controlling drones. Our goal is to develop a voice command drone system capable of comprehending and responding to randomly spoken Bengali voice command. To achieve this, we will train an artificial neural network model and deploy it on a control device. In our pursuit, we are building a comprehensive dataset that encompasses diverse Bengali voice commands, taking into account variation in environment, accents, and speakers. We will then rigorously evaluate the performance and effectiveness of our proposed model, ensuring it meets the highest standard. By accomplishing this objective, we aim to contribute to the broader field of multilingual applications. Ladies and gentlemen, let's take a quick look at related research. EFPC Club et al. Used a convolutional neural network for Turkish voice command, while Faizi et al. Achieved 88.57% accuracy with a hidden Markov model-based Phoenix open source space recognition system. Contreras et al. Employed two different approaches to classify English and Spanish voice command, whereas Lecture et al. Explored Thai voice command. We'll now explore Bengali commands and artificial neural networks in our research. Let's delve into our methodology, a journey in a few key steps. We started by recording randomly spoken Bengali voice command using a microphone, building our own dataset. Next, we pre-process the audio data to extract essential features to ensure the robustness of our model. We split the dataset into three sets: train, validation, and test. The training set was used to train our artificial neural network model, and the validation set is used for validating it. Okay, then we rigorously tested the trained model with the unseen test set, generating a classification results. Finally, we assessed our model's performance using various metrics, painting a comprehensive picture of its capabilities. In the realm of data collections, we have compiled a robust but compact dataset. It comprises 6,010 Bengali audio sample featuring diverse accent, environmental conditions, and voices, including both male and female speakers. This recordings encompasses 15 unique commands, which are shown in the table on the right of the slide. Collectively span the 3.5 hours, where each audio file is averaged at 2 seconds in length and sampled at a 44.1 kilohertz sampling rate. The dataset obviously is stored in the MP3 format. In the cornerstone is the cornerstone of our research. In the pre-processing, we begin with the pre-emphasis steps, employing a high-pass filter to enhance the high-frequency component and reduce noise from our audio data. We segmented the signal or audio data into 25 millisecond frames, ensuring a smooth transition to ensure with a Hamming window. Fast Fourier transform is then used to estimate the power spectrum of each frame. We applied the Mal filter bank to the power spectrum, summing the energy in each filter. Afterward, we logarithmize this filter bank energies, applying the discrete Hossain transform, and finally extract the Mal frequency sequestral coefficients or MFCCs from the DCT coefficient. This extracted MFCC coefficients serve as the feature for the training of our artificial neural network model, enabling it to understand and classifying the audio command accurately. Here is the data split approaches. We in this slide we have employed two different approaches for this. Okay, the train validation test split and a 6-fold cross validation approach. In the both approach, we allocated 70% of data for training, while another 15% is dedicated to both validation and testing. Here is our artificial neural network model architecture. Artificial neural network consists of multiple layers of interconnected neurons. We have employed a 4-layered artificial neural network model consisting of an input layer with 45 neurons, two dense layer with 2,048 neurons each, and an output layer with 15 neurons. To mitigate overfitting, a dropout value of 0.6 was utilized in each dense layer. As training parameter, we used ReLU and softmax as activation function in the dense and output layer, respectively. For multi-class classification, we employed the categorical post-cross and tropic post function. The training process spanned 500 epochs with a batch size of 64, utilizing the Adam optimizer for efficient gradient descent convergence. Here is the proposed model architecture, which functions as a remote. It primarily comprises a Raspberry Pi, a USB microphone, a push button, and a transmitter component, as outlined in the system architecture. The USB microphone connects to the Raspberry Pi via the USB port of Raspberry Pi, while the push button and the transmitter are connected to specific pins. Within the Raspberry Pi, our train model is deployed to recognize randomly spoken Bengali voice command for drone control. Simultaneously, the drone receiver receives the transmitter signal using the transmitter. This slide illustrates the functionality of our remote control system. Here, user press the push button to start recording voice commands and press it again to stop. We then extract frequency substrate coefficients features from the recorded commands. These features are fed into our artificial neural network trained model to obtain prediction. The predicted commands is mapped to a specific voltage level, which is then transmitted to the drone receiver to initiate actions. Also, here is the most crucial part of our presentation. Confusion matrix is the essential to provide a visual representation of classification performance by counting correct and incorrect prediction, facilitating the calculation of various performance metrics like precision, recall, F1 score. On the left side of the slide, as you can see, 15 by 15 score matrix, which represent the confusion matrix obtained in our basket scenario in our research. We have derived a comprehensive classification report from the previously displayed confusion matrix. This report provides insight into precision, recall, F1 score for individual classes, alongside a micro average, weighted average, and sample average. Additionally, it includes the number of subgroups instances for each classes in a separate column. In the six-fold cross-validation accuracy report, we have displayed the training, validation, and testing accuracy for each round. The average accuracy across all rounds resulted in 71.97% for testing data set. However, in test train validation test approach, we have tested a higher accuracy of 73.16% in testing, indicating its superior performance compared to six-fold cross-validation. In this slide, providing visual insight into our results, it's displaying epoch versus accuracy graph for both approaches, allowing you to observe the training progress. And the next slide it showcases the rock of curves for the micro averages and each class versus all scenario. Here is the analysis. In our optimal case scenario, we achieved a testing accuracy of 73%, which, while not ideal, is influenced by several factors, contributing to a decrease in accuracy. We have discovered those factors, primarily the dataset size and quality, which significantly influence accuracy. Additionally, noise from the environment and the settings during voice command recognition played a crucial role. Improved noise removal technique proved highly effective in enhancing accuracy. Furthermore, variation in speakers' accent, speaking speed, style, age, and other factors contribute to differences in delivering the same commands. Lastly, the choice of pre-processing techniques such as spectrogram or log spectrogram or MFCC significantly impacts the model's robustness and generalizations. So in our future endeavor, we aim to enhance our research by expanding our dataset, implementing advanced noise removal technique, and refining commands processing systems capable of handling multiple voice commands simultaneously. Our primary focus is on creating a multilingual drone control system that allows users to communicate naturally in their own language without the constraint of predefined commands. In conclusion, our research introduced an innovative drone control system that responds to spontaneous Bengali voice commands, streamlining drone operation and increasing accessibility. We are aiming to develop an enhanced drone control system that addresses the challenges encountered in this study, resulting in more accurate and efficient multilingual voice command operated drone. Here is the references that used throughout this presentation. And finally, thank you for your attention and time. Any questions and insights are welcome. Thank you. Yeah.